Again, welcome to Data Structure and Algorithm course. In this lectures, we're going to discuss about graphs, which again cover our course textbook, chapter 14. So a graph is a pair of V and E. V represent the vertices, and a vertices is a set of nodes. And also E represent the edges. So here we say E is a collection of pairs of vertices. So we have an example of a graph here. The vertices are the SFO, ORD, and PVD, and these are airport code. And the edges are the line that connect the airport codes. So for example, we have edges from SFO to ORD, which is 1843. This 1843 can represent the flight number or the marriage from SFO to ORD. So here we see an example of a vertex representing an airport, and it stores the 3-letter airport code. An edge represents the flight route between the two airports, and also it can store the marriage of the route. So again, the vertices, or sometimes we use the term the node, represent the airport, and the edges is the route or the distance between two airports. In a graph, we have two types of edges. We have the directed edge. A directed edge normally will point to the direction that we are moving from. So from the source or the origin to the destination. So example here, this is a directed edge because our origin will be ORD. The flight is from ORD and is going to PVD. So PVD will be our destination. So we can see the arrow coming from ORD pointing toward PVD. So again, the ORD will be the origin, and then the PVD represent the destination. The edge here represent the flight number AA1206. Now in the second one, we have undirected edge. So undirected edge means we can go either direction. The route can be from ORD to PVD or PVD to ORD. And this is a nice example here. So 845 miles represent the distance between the two airports. So the distance is the same if it's from PVD to ORD. It's also the same is from ORD to PVD. So this is again undirected edge. And also we may use the term as undirected graph. Here we have a directed graph because if all the edges in the graph are directed, then it's a directed graph. And here, if all the edges are undirected, then it's undirected graph. So this is a good example, a flight number AA1206. It has to go to only one direction at a particular point of time. So here we represent from ORD to PVD. But the distance can be the same at any direction. So the definition here, we say the directed graph when all the edges are directed. So example will be a route network. Undirected graph means when all the edges are undirected in the graph. An example is a flight network. So we have examples of applications in graph. And the first example we have here is electronic circuits. So electronic circuits can be represented as a graph, which again consists of the vertices and the edge. So the vertices will be the electrical components. The edge can be the wiring system that connects two electrical components together. So example given here is the printed circuit board or integrated circuit. Another example is a transportation network system. So we may have a highway network, and normally highway network, the vertices will represent the cities or the source, and also the edges represent the distance between the city or from source to destination, the origin to destination. A good example we saw previously was the freight network also. which in this case can represent the different airports, and the edges will represent the distance between the airport or the route. Also, an example would be a computer network, such as a local area network or the internet or the web. So example given here is a computer network. For example, we have ADT.net connected to brown.edu, connected to qwest.net, and John, David, Paul are connected to the core. So the sources are the computers and also the components, and the edges will be the connections. Also, example can be a database system like entity relationship diagram. Normally in entity relationship diagram, the entity will represent the vertices. Relationship are normally a line and we represent as the edges. And in entity relationship, we have with database system, we have three types of relationship, like one to many, many to many, many to one. And this will be represented as the edge. And the entity, which later becomes the table or the object itself, represent as the vertices. So here we'll go through some few terminology here. The first terminology is what is the end vertices or endpoint of an edge. So the endpoint of an edge will be an example of, and the diagram we have here, we have vertices U and also vertex V, U and V. So the U and V, they have endpoint at A. So we say U and V are the endpoint of A. So edges A, the endpoint of it is U and V. Also, we use the term edges incident on a vertex. So that will be the edges. So for example, here we say A, D, and B are incidents on V because the edges A, D, and B are connected to V. So we said A, D, and B are incidents on V. So that's second edges incident on vertex. Also, we have the adjacent vertices. Adjacent vertices are vertices that are connected to the with the same edge. So for example, we can say V and X are adjacent vertices because they are connected with HB, connected to. Now, V and Z are not adjacent vertices because there's no edge connected between V and Z. Also, the degree of a vertex will be the number of vertices, the number of edges connected to the vertex. So for example, the degree of vertex V is 3 because we have 3 edges connected to vertex. And also the degree of vertex Z will be 4. When you have a loop or self-loop, it represents 2. So we have one edge, H, another edge, Y, I, that is 2, and then the self-loop is 2. So the degree of vertex Z is 4. We may also have a para edges as H and I. A para edges means the 2 edges are para if they are connected to the same vertices. So we can see H and I are connected between X and Z. Then we have the self-loop, which means the edges connected start from one vertex and end at the same vertex without going through any vertex. So here the Z here have a self-loop of J because J starts from Z and it ends at Z without going through connected to any other vertex. There's no any other vertex set from Z back to Z again. So those are the terminology: end vertices, edge incident on a vertex, adjacent vertices, degree of a vertex, para edges, and also the self-loop. So the next terminology will be what is a path. So a path normally will be the sequence of alternative vertices and edges. So a path normally will begin with one vertex and it will end at another vertex. So a very good example here, we have a path from vertex V to Z. and the path is V, B, X, H, Z. We also include, we start with the vertex name V, and we go through edges B. So we're going to have VB, then we go to vertex X, then edge H to Z. So we will call that path P1. So P1 path is V, B, S, Z. So again, the path is a sequence of alternative vertices and edges. We always begin with a vertex and we have to end with a vertex. So we start with V, we end at Z. Then each edge is preceded and followed by its endpoints. Now we have two types of a path. A simple path is a path such that all its vertices and edges are distinct. Then that's a simple path. So the example we show V, B, X, H, Z is a simple path because again, all the vertices and edges are distinct. Now we have a P2. P2, we go from U to C, edges C to W. Then we go E, edge E to X. Then we go G to Y. Then we come back to W, and we go to D, and we end up at V. So here we can see that we went through W twice, at least. So it's not distinct. We say a simple path. It's a path such that all its vertices and edges are distinct. So P1 is a simple path because all the edges and vertices are distinct. But P2 is not a simple path because the edges, actually the vertices also are not distinct. We have W twice. So we also may give an example of what we call the circle. So we can say circles is a path. So we can see an example here, C1. We start from vertex V and we end at vertex V, but this time we go through some edges. Now, if we start at V and we end at V without going through any vertices or any edges, then we have what we call the self loop. This is a circle or a simple circle because we have more than one vertices and more than one edge going around. But where we start, we end at that place. So we start at vertex V and we end at V. So we say a circle is a circular sequence of alternating vertices and also edges. Now, each edge is preceded and followed by its endpoints. And the whole idea of a circle is that where you start, the vertex that you start at, you are going to end at the same vertex. So a simple circle will be a circle that such that all its vertices and edges are distinct. Same concept as path. So example, we have from V, B, X, G, Y, FH to W vertex, CH to U, then AH back to V. This will be a simple circle because all the vertices and the edges are distinct. They appear only once. Now we also have C2, where we are starting from U. So we start from U to C to W and to E to X, then G to Y. Then we go to F. F is the edge to W. Now we went through W twice already. Then we go to D and come back to E. So this is not a simple circle because the vertices are not again distinct. C1 is distinct because we visited all the edges and the vertex once. If it's not simple, same as path. If a path or circle is not simple, it means we visited the edge, at least one of the edge and vertices was visited more than once. at least once. More than one vertex or edge was visited more than once. So these are some of the properties of a graph. We have the first property 1. We say the degree, the sum of the degree of vertex is always 2m. Again, we say the degree is how many edges are connected to the vertex. Now, to prove this, we say that each edge is counted twice. So that's why it's 2. M represents the number of edges, and N will represent the number of vertices. So in this property, when we say M means the number of edges we can have, N is the number of vertices. So the first property says the sum of the degree of the vertices is always 2 times M. M represents the number of edges we have in the graph. To prove this is very straightforward. We know that each edge is counted twice, each edge. Now, the second property says that in an undirected graph with no self-loops and also no multiple edges, like a para edges, in this case, then the M, which is again the number of edges, is always less than or equal to N times N minus 1 over 2. Now, to prove this, we can say that each vertex has degree at most N minus 1. So if N minus 1 is at most for each vertex, we multiply by N, how many vertex we have, we divided by 2. And that again will represent the M. The edges should always be less than that or equal at most. So the example is given in this graph. You can see we have four vertices. We can see that the maximum degree we have is 3 for each one. So N is 4. And this is the maximum degree we can have for each node. So when we count the number of edges, it will be 6. We have 1, 2, 3, 4, 5, 6. So which means at most the degree of V is 3, the degree of any vertex here is again 3. Now next is the vertices and edges. As we said earlier, a graph again consists of vertices and edges, or here we say a collection of vertices and edges. Now we can model the abstraction as a combination of 3 data types. We should have the vertex, we should have the edge, and also the graph. So a vertex will be the lightweight object that stores an arbitrary element provided by the user. So an example can be an airport code, as we saw earlier. Also, we assume it supports a method element to retrieve the stored element. Also, an edge will store an associated object. Example we saw previously was a flight number, or the distance travel, the marriage, or the distance between 2 airports. Also, the cost of the flight from one point to another that can be associated with edge. And this can retrieve with the element method. Now, next we shall go through the graph ADT. Again, when we do the coding, we will implement all this. So for example, in the graph data structure, these are the possible operations or the methods that we can perform on the graph. So for example, the first one is num-vertices method. Num-vertices method will return the number of vertices of a graph. And also we have the method vertices. This will return an iteration of all the vertices of the graph. Then we have the num-edges. Again, that returns the number of edges of the graph. Then we also have edges method, who returns an iteration of all the edges of the graph. Then we also have get edge. which takes argument of U and V. U will represent the origin vertex, and V will represent the destination vertex. So we are getting the edge. What is the edge between U and V, or any two vertices in a graph? So this method again returns the edge from vertex U to vertex V, if one exists. If it doesn't exist, then it will return null. Now, for an undirected graph, there is no difference between get edge UV and get edge VU. As we said earlier, undirected graph means we can go either direction, from destination, source to destination, or opposite destination to source, either direction. We also have the method n vertices. This will return an array containing the two endpoint vertices of an edge. So that's why the argument is the edge. Now, if the graph is directed, then the first vertex will be the origin, and the second vertex will be the destination. Now, if it's undirected, we don't care, because either one can be origin and destination. Then we also have a method opposite, which takes V and E as arguments. Here for edge E, incident to vertex V, this method will return the other vertex of the edge, or an error occurs if E is not incident to V. And then we have the out degree, returns the number of out, and this is for directed graph, out degree. Then we have also in degree, because previously we were discussing about the degree. In this case, we say the degree will be the number of edges, but here it's undirected, so we don't count out or in. Now, if we have a directed graph, we may say the arrow pointing from A to B or from B to C. So if it's A to B, then it's out degree. If it's from B to into C and I'm at C, then that will be in degree. So those are the two different. So we can have out degree returns the number of outgoing edges from vertex V, but the in degree will return the number of incoming edges to vertex V. The argument can be any vertex. Here we are using vertex V. Now the outgoing edges V, same thing, it will return an iteration of all outgoing edges from vertex V, because our argument is the vertex V. Same thing, incoming edges for V, it will return an iteration of all incoming edges to V. But for an undirected graph, this returns the same collection, since again, undirected graph, we can go either direction. Also, we have a method to insert vertex. So this will create and return a new vertex store element X. The argument is X. Or in store edge, then we are going to store edge between U and V, and the edge name is X. So this will create and return a new edge from vertex U to V, because U comes first before V, storing the element X. And this means an error occurs if there is already existing an edge from U to V. So we also have the method to remove vertex, that remove vertices V and all its incidents. That is again the edges connected to it from the graph. And also we have remove edge, which is to remove edge E from the graph. So again, we can implement all this in our graph class. So this is an edge list structure. Here we say the vertex object may have element and also reference to position in vertex sequence. With an edge object is an element, we may have the origin vertex object. We may also have the destination vertex object. Then reference to position in edge sequence. Then we have the vertex sequence, which is again the sequence of vertex object. Then edge sequence also will be the sequence of edge. So example here, we have again a graph. This graph consists of 4 vertices U, V, W, Z. The edges are E, G, F, H, lower cases. So this represents again our graph. And also we have a second one. Also the same U, V, W, Z. So first graph is undirected. Second graph, we can see the edges have an arrow. So this is directed graph. So for example, in U here, we have 2 degrees, E and G, 2 edges. So the degree is 2. But here we have incoming 3 edges, so 3 degrees. So that will lead us to what we call the adjacency list structure. We can represent graph as an adjacency list. So here we have again the graph with 4 vertices, U, V, W, Z. We can represent it as an adjacency list, either using an array or linked list. So let's assume here we are using an array. So what we normally do is that the number of elements here should represent the number of vertices in the graph. So in this graph, I have 4 vertices. So that's why we have 4 items here. Let's say a linked list or array. Now, the items that will go inside the box here will represent the edge. So for example, this is an undirected graph. So we will assume we'll use all the edges at any point in the vertex. So for example, the first we are in the vertex U. When we are in vertex U, we have edge E to V, G to W. So that's why we have E and G. So U represent E. Again, we don't need to show the direction here because this is undirected graph. Now, in terms of V, we have E and F. So that's why we have E and F here. And in terms of W, we have GHF or FGH. So that's why W have FGH. In terms of Z vertex, we have only H edge connect. So we have only H. We can also represent a graph as an adjacency matrix. So those are the 2 main representation of graph, as either as an adjacency list or adjacency matrix. So with adjacency matrix, almost the same concept as list, but we know matrix consists of rows and columns. So a matrix may have the number of rows and columns. Now the size of a matrix depends on the number of vertices we have. So always when we represent graph as a matrix or adjacency matrix, the matrix will be square. The number of rows is the same as number of columns. So here we have 4 vertices, which means our matrix will be, the size will be 4 by 4. So we have 4 U, V, W, Z. We represent them here. So U will be 0, V will be 1, W will be 2, Z will be 3. And also at the column 0, 1, 2, 3. Again, the reason why 0, 1, 2, 3, 4 by 4, 4 rows, 4 columns, because we have 4 vertices. Now I'm at U now. When I'm at U, this is undirected graph. It means from U to U will be 0 to 0, since we say U is 0. You see that we don't have anything because we don't have no self loop. If we have a self loop, it will be 2. Now from U to 1, 1 represents V. So from U to V, we have edge E, which is right because in the graph U to V, we have edge E. Then we have from U to the third and second is W. So U to W, we have G. So U to V, we have E. Then the Z is 3. U to Z, 3, there's nothing. So we leave it. Then we move from U to V. Now, when we are at V position, from looping, we don't have anything. So you can see the diagonal 1 to 1 is nothing. Now from V to U, U is 1. So from V to U, we have E. I mean, V is 1, U is 0. So 1 to 0 is E. Now we have W is 2. So from V to W, we have F. So 2, we have F. And we don't have V to Z. Z is 3. So we leave there empty. Then we move to 2, which is W. So we start with 0 first. W to 0, we have G. Again, this is undirected graph. So we may have U, W, and W to U. So that's why we write the G here. Then we have W to V. V is 1. We have F. Now W to W, we have nothing. So we leave it empty. W to W means self loop. Then W to Z, we have H. So we have the H. Now, when we look at Z at 3, Z is not connected to 0, U, so we leave it. Z is not connected to V, we leave it. But Z is connected to W, so we have H. Then Z is not a self loop, so we leave that empty also. So that's how we represent, again, a graph in adjacency matrix. Now, the size of the matrix, as we said earlier, depends on the number of vertices you have. So this is the performance of our graph. So here we let N represent the number of vertices, M will represent the edges. In this graph, we don't have any parallel edges. We assume there's no parallel edges and there's no self loop. So what is the space? The space will be the memory size that each graph may occupy. Now, the total space together, edge list will be N plus M. Again, the number of vertices plus the number of edges will give us the edge list. In terms of adjacency list, we also have N plus M because it's linear. But when it comes to adjacency matrix, it will be N squared because we have the number of rows and columns. So if the vertices are 4, the possible boxes we may have will be 16 because 4 by 4, 4 rows, 4 columns. So that's why it's N squared. 4 squared is 16. Or if the vertices we have is 10, then it will be 10 by 10. So 10 squared will be 100. So in terms of space, adjacency matrix is N squared, the number of vertices squared. We can see that adjacency list take less with edge list, and plus we had the total of number of vertices and edges. Now, when we talk about the incident edge at V, the number of the edge list will be M because M will be incident. Remember, we said the incident is the number of edges, incident edges, number of edges connected to a particular vertices. So it will be the number of the M. Then the degree of V also with adjacency list, it will be degree of V. Now with adjacency matrix will be the number of edges, vertices we have, so N. And also if you are looking for adjacent, the same thing M, we may have a minimal degree for V and also the degree for W. And in terms of matrix, it's only 1. Insert vertex is 1 time 1, 1, but with adjacency it will be N squared. Insert edge is 1 for edge list, 1 for adjacency list, and 1 for adjacency matrix, because we are inserting the edge. Then to remove a vertex with edge list, the space it occupies the number of edges we have. The adjacency list will be the degree of V. Then with adjacency matrix, removing vertex will be N squared. And the last is remove edge, which take the argument of the edge. With edge list, it will be 1. With adjacency list, it will be 1. And with adjacency matrix also is 1. So this will be the conclusion of our lectures in graph. And this is the beginning of our graph section, the course. So we cover the terminology and also the definition. So again, see you in the next class, and thank you.